And welcome back to our discussion of experimental design. Okay, so to summarize where we've come so far, you may remember we have a sample of individuals who is randomly assigned to receive either our independent variable manipulation or a control group, and then we measure them on the dependent variable, and we look to see if there's a difference in those scores. And maybe there's 25 people in each group. That's just a random number I'm throwing out there. So let's think this through a little bit with what we've been talking about in the standard normal distribution. Based on what we know, how can we determine if these scores are from the same population or not? If the experimental group and the control group are from the same or different population. Remember, all samples have some degree of error. So even if I drew those samples from the same population, for example, we have our class. The class average on the last exam was 65 or 64, whatever it was. And I draw two samples of 5 people. We don't expect their means to be identical, even though they came from the same population. Why? Because of sampling error. So how can we tell if they came from the same class or not? Because we never know truly what the actual population is, or we never know truly whether they came from the same population. We are hypothesizing, in fact, that they don't. Well, hopefully it's becoming a little clearer, but if not, this is where that standard normal distribution comes in. Because if you remember the sampling distribution of means, that is, repeated samples taken from the same population, are going to have a mean of mu. So let's suppose that we know what mu is in this example, and so our control group, or our group that's down here, is really just going to be mu. We're going to compare our experimental group to mu. If I draw a sample, my null hypothesis says that that sample came from this population with mu as its mean, and my research hypothesis says that it came from a different population with a different mu. So we have our sampling distribution of means. How can we use that to decide which of those two hypotheses is correct? Well, remember that in the sampling distribution of means, 68% of the sample means are going to fall within one standard error of the mean above and below mu. And 95% of the sample means are going to come within 2 standard errors of the mean. 95% of the time. So we can use those probabilities and the more exact probabilities in the z-table of your text to tell us how likely it is that an individual came, or a sample came from that population. If the sample, let's say we get a z of 0.5, we can look up in the textbook and find out the probability of finding a score that is half a standard error away or more. And if we do that, if z equals 0.5, we can see that the probability of getting a 0.5 or greater z-score is 0.3085. Okay, there's a 30% chance of finding a sample from this population that is a half a standard error away from the mean, and that's pretty common. But what instead if my sample of kids who watch a violent movie scored, had a z of, we'll say, 2.3. Well, if I look up 2.3 in the z-table, I will see that the chance of drawing a sample whose score is at least that far away from the mean is 0.0107. Okay, that means there's about a 1% chance, one time out of 100, would we find a sample whose individuals are all so extreme that their average score is 2.3 standard errors away from mu. And in science, we tend to think of rare events as, not likely to happen. This is a probability judgment. If it is something that is not likely to happen, we are going to assume rather that they did not come from population, this blue population, but instead are members of some other population with their own mu, because it is more likely that they came from a population whose mu is much closer than the one that we're comparing them to. So that's how we're going to use the standard normal distribution and probability to make inferences about the way the world works, by looking at how likely it is that we would get a sample a given distance away from the mean of the population. So by way of an example for that, looking at slide 29 on the lecture notes, so let's carry out an experiment. This is actually one that's displayed on the lecture notes. We have an experimental group who takes part in our experiment, and they get a mean on my dependent measure of 53.32. Whatever it is that we measured, that's their score on it. And the number of individuals in that sample were 50. Then we are going to compare them to a population that has a mean of 50 with a standard deviation of 10. My question now is, did this sample of 50 individuals come from this population? Well, how can we figure that out? Well, we have to calculate, or we get to, because we have both mu and sigma, we can calculate a z-score. Now, you may remember that our z-scores are x minus mu divided by sigma, which tells us the number of standard deviations away from the mean a given score is. Well, we can apply the same z formula, again that's for individuals, we can apply that same formula to samples, and the formula changes only slightly. The formula is we take the mean, in this case mean, minus, oops, I got a spare, there we go, mean minus mu divided by, what are we going to divide by for samples? Well, not the standard deviation, because that's the average amount that individual scores differ from the mean. We're going to divide by the standard error of the mean. And we're still going to get a z-score. It tells us the same thing. It tells us the number of standard errors away from the mean our sample fell. And remember that standard error of the mean is the standard deviation divided by the square root of n. So for this example, we have a standard deviation of 10, and we have a sample of 50. We're going to take the square root of that, and 10 divided by the square root of 50 is 1.414. So that's our the denominator there. So to set this up, we have z equals 53.32 minus our mu of 50 divided by 1.414. And when we do that math, we get a z of 2.35. What does that mean? That means that our sample of 50 people who had a mean of 53.32 fell not 1, not 2, but 2.35 standard errors away from the mean. And how likely is it that we would get, by randomly drawing a sample from this population with a mean of 50, that's our mu, and we had an x bar of 53.32. How likely is it that we would get a sample through random selection that is 2.35 standard errors away from the mean, well, that probability is 0.0094. In other words, there's less than a 1% chance. There's a 0.94% chance that we would draw a sample at random from this population and get a mean of 53.32. That's pretty rare, less than 1%. And here's the thing, I'll try and squeeze it in here in a different color. In science, we've come to a general agreement that for the most part, anytime the probability of finding a sample by chance alone is less than 0.05, less than 5%, then we conclude that it's not likely to have come from that population. It's more likely that there was some other population out here whose mu was much closer to the one that we drew. So in this case, that's pretty rare. That 0.0094 probability tells us that our sample didn't likely come from the population with a mu of 50 and a sigma of 10. It likely came from some other population. And this brings up the concept of statistical significance. Statistical significance. So significance in statistics means that the difference that we observed is real. It is reliable. It is something that if we were to repeat the experiment, we should find a very similar difference between the population and our sample. In other words, it's not due to just sampling error. And as I said, in science, any time that a sample mean would differ from mu, or from different groups, less than 5 times out of 100, that is 5% of the time or less, we reject the null hypothesis and conclude that the sample came from a different population than the one that we're comparing it to. So this p of less than 0.05 is very, very important. And if for the z distribution, anytime z equals 1.96 or more, the difference is significant. Remember what that means. If we have the standard normal distribution with a mean of mu, if you look in the table in the back of your book, if you go out 1 and not quite 2, but we go out to z equals 1.96, you will see that that is where 5%, well actually 2.5% of the population falls. Why 2.5? Because we can also go below the mean 1.96 z-scores, minus 1.96. And that also is 2.5. So 2.5% of the population falls, of the means fall 1.96 standard deviations below the mean, and 2.5% of the sample means are going to fall 1.96 standard errors above the mean. And together that equals 5%. So when we find a sample that is out in one of those two extremes, we know that it would happen fewer than 5 times out of 100. And that's when we reject the null hypothesis and say that the difference is significant or real. Now, if instead we drew a sample and it was closer than 1.96 standard error units away, anywhere in that zone, okay, in that case p is greater than 0.05. We don't have to know exactly what it is. We can look it up in the table, but as long as it is greater than 0.05, then we fail to reject the null. That means we cannot rule out the null hypothesis as viable, and we conclude that it's possible that those samples came from this population. If we reject the null, we look around and say, well, if it's not the null hypothesis, what else could it be? It must be the research hypothesis. But if we can't reject the null, we're not saying that the null is true. All we're saying is we don't have enough evidence to rule it out as a possibility. Okay, I just got done hinting at this next little topic here. Remember, if we reject the null hypothesis and say that the difference is significant, we haven't proven the research hypothesis. We just say we found support for it. Similarly, if we fail to reject the null, we haven't proven the null hypothesis. We just failed to find enough evidence to exclude it. It's all based on probabilities. Some things are more probable than others, but we haven't proven anything, which means there's a chance that we are wrong. And so I wanted to discuss now about what happens in those situations, or what do we call those types of errors. So I just put up an image that's actually contained in the slides that describes those types of errors. And let me explain this to you. So in the real world, if we were omniscient, if we knew what the populations were like, that's what's happening on the top half of this figure. Since all statistical tests are a direct test of the null hypothesis, in the real world, the null hypothesis is either true or false. One of those has to be true. Okay? We never know which it is, but there is an objective answer out there. We just can't test the entire population and figure that out. So let me clean this up a little bit. Now what happens instead is that we are operating on the left side of this diagram here. We have to make a decision based on our sample data. And that decision is either to reject the null or fail to reject the null. So there is an objective truth out there, and we're making a decision trying to estimate or infer what that truth is. If we reject the null, again, I'm going to clean this up a little bit. If we reject the null and we say that a difference that we found is significant, not due to sampling error, and in fact the null hypothesis is false, we've made what is called a hit, or at least a correct decision. And we're excited. Yay! All right, we said that the difference between kids who see violent movies and the general population is real. Kids who see violent movies do behave more violently than those who don't see violent movies. And if that were true in the real world, we would have made a correct decision. We don't know for sure that we did, but that would be a correct decision. But what if, in fact, we just happened to sample, because all possible combinations can occur, a group of kids who were innately more violent than others, and it wasn't the movie that caused them to be more violent? Well, we would have rejected the null, but if the null hypothesis were in fact true, and kids who watch violent movies don't behave more differently than kids who don't watch violent movies, we will have made what's known as a type 1 error. So a type 1 error is rejecting the null when the null is true. Okay? The probability of making a type 1 error is always equal to your cutoff point. Your cutoff point in most of the science is 0.05. In other words, whenever we reject the null, because the difference that we found would occur fewer than 5 times out of 100, that means 5 times out of 100 we will have been wrong, because the difference occurred just because of sampling error. So we gambled a little bit. We said, no, it's not likely to be. Our sample is not likely to have come from this population because it was way out in the extreme here. But 5% of the time, there is going to be a sample that is way out in one of those two extremes. So we will make a type 1 error about 5% of the time. Let me clean up the ink. Okay. Now let's look at the other type of error. First of all, if we fail to reject the null, if we say that there is nothing more than probability, or nothing more than chance, that is accounting for the difference that we observed. So we say we cannot rule out the null hypothesis. And in the real world, if the null hypothesis is true, then we made a correct decision. Once again, yay, no harm. Okay? We say, nope, the difference isn't significant. Kids who watch violent movies don't behave any differently beyond just normal variation. We will have made a correct decision. But what happens if instead we failed to reject the null hypothesis, but in fact the null hypothesis is false? That is, kids who watch violent movies, really do behave differently. In that instance, we will have made a type 2 error. Okay? And we just call it a type 2 error. Now, calculating the probability of making a type 2 error is a little more complicated and not important for our purposes. But it's vitally important that you know the difference between a type 1 error and a type 2 error. Anytime you reject the null, anytime that you say a difference is significant, that's a G, then you might be making a type 1 error. You can't make any other type of error. You might be right, but you might be making a type 1 error. Anytime that you fail to reject the null hypothesis, or say that it is non-significant, then yes, you might be correct, but you might be making a type 2 error. You can't be making any other type of error in there. Now, we never know. First of all, let me emphasize, you have to just flat out memorize this. Okay? A type 1 error is saying the difference is significant when it is not. And a type 2 error is saying a difference is non-significant when in fact it is. Okay? You've made a mistake. Now, my question to you is, how do we know when that's happening? How do we know if we've made a mistake? Well, at any given instance, we really don't. This is where, in research, the concept, or the scientific method, the concept of replication comes in. So anytime a new finding comes out in the literature, somebody says, hey, this variable has an effect on that variable. We found a significant difference. Yay! Okay, researchers say, okay, that's really interesting. However, there's always a chance that you made a type 1 error and just happened to find a sample from this population that behaved, uniquely or differently. But they really did come from this population. So we must replicate or repeat the study and see if we get the same finding again. And if we repeat the study again and find a group that also behaves out in the extreme range, and even more, if we find a third sample that behaves out in the extreme, it is, always possible to find one group who's far away. But to repeat the experiment multiple times and always get an extreme score, it's becoming less and less and less probable that those samples all came from this same population. It's more likely that they came from some other population. And so we have more confidence that we did not make a type 1 error. So the key to discovering what type of error you made is to see if you made an error is replication. It's similar to our homework assignment from a little bit ago, where I said if you draw a marble out and it's white, what would you guess the population of marbles is? And you would say white. And then I asked you, how would you test that? Okay, you would reach in and grab another marble and see. So that's the same process. Replication is a way of testing to see if our conclusion was incorrect. So in summary, here is kind of a walk through the scientific method and experimental design issues. Step 1, we want to review the literature and develop a testable hypothesis. And I defined what testable is a little bit earlier. Your book goes into the same as well. And anytime you develop a research hypothesis, the null hypothesis is implied. The null hypothesis being that there's no difference or no effect of your IV on your DV. We then need to set a level of significance. And I told you most often that level of significance is 0.05. which means anytime a difference would occur fewer than 5 times out of 100 by chance alone, just because of sampling error, that's when we're going to reject the null hypothesis. That's when the score is way out into this extreme zone. Now, 5% is kind of the minimum difference. You'll read in your textbook more that sometimes we want to set that difference to be even more stringent, even further out into the extremes, like 0.01. Anytime we get a sample that would occur by chance 1% of the time, or less than 1 time out of 100, then we would reject the null. So you'll read about that decision-making process. But nonetheless, before you design your experiment, you want to set up your alpha level, your decision-making. And I also remember for z-scores, 1.96 is that point where scores would occur fewer than 5 times out of 100. And that's what step 3 is, identifying that critical value. In the case of z-scores, 1.96 is how far away from the mean you would be in standard error units to occur fewer than 5 times out of 100. Anything beyond that would occur fewer than 5 times out of 100 by chance alone. 2.58 would be the critical value that would occur 1% of the time. So if your score was larger than 2.58, then you're into that less than 1% zone. Step 4 is once you've collected your data, you calculate your test statistic, in this case a z-score. And whatever your z is, you compare that in step 5 to your critical value. If your z is larger than your, not alpha, but your critical level, so I'm going to say critical value, then you reject the null. You are further out, there we go, further out into that extreme range. If your z falls short of that, then you fail to reject the null. So you make a decision. I want to make one last quick comment about this concept of the critical value. If you remember, I said that a z of 1.96 is where the probability is less than 0.05. That means that when a sample mean is not 1, but 1.96 standard errors away from mu, then we're in that zone. Any score beyond 1.96 would occur less than 5 times out of 100 in either direction, right? Negative 1.96. So 1.96 is our critical z. That's the score that we're looking for to be able to reject the null. That concept of the critical value, if it helps you remember, is kind of like those signs that you see at amusement parks and the fair and Disneyland and so on that says, you have to be this tall before you can go on the ride. In science, you have to be this far away from the mean in order to reject the null. That's what we mean by significance. So our critical value in this example is 1.96, and you want your score to be greater than 1.96 to reject the null. If you do have a score that is greater than 1.96, you've obtained a p-value of less than 0.05. The probability of finding that result is less than 5% of the time. So that's discussed in more detail in your textbook, but I just wanted to give you that little metaphor if it helps you remember things. And that's going to conclude our discussion of experimental design and experimental decision making using z-scores. Okay? Thanks for watching.